Good evening, guys. Those who are online are able to hear me?
Yes, sir.
Yes, sir.
1 minute. Yeah, can someone speak now? Are you able to hear me?
Yes, sir.
Yes, sir.
Yeah. Now can someone respond, guys?
Yes, sir.
Yes, sir.
Perfect. Just a minute. We'll get started. Yeah. So last class we saw what are electric field lines or lines of force, right? So now we'll see the next concept, that is the properties of these lines of forces. Right. So we need to understand what are the properties exhibited by these kind of lines. Okay. So last class, if you remember, I showed you a simulation. So in the simulation, I told you where does the electric field start and where does it end and all those things, right? So where does it start, guys? So electric field lines start from the positive charge and they terminate at the negative charge. So they do not form what? They do not form closed loops at all, like magnetic field, right? Similarly, if you take two lines of force, that is, you take two electric field lines, they are never going to intersect. Why is it so? Yeah. So generally, this is the question. If you have an electric field line for that matter, so if you take at a particular point, right? So at that point, you want to find the direction of electric field. What will you do? So you will draw a tangent. So tangent is a line which gets extended in both the directions. But what direction will you assign to this tangent? Along the direction of electric field. So this is the direction of electric field at the given point. So if there is a scenario where two field lines are meeting, what would happen? So this is a very, very important point. They'll ask you, why is it so? Why can't two lines intersect? The answer to that is very simple. Two tangents can be drawn at the same point, right? So the next line says something related to tangent only. The tangent to a line of force at any point gives the direction of electric field at that point. So this is a known fact, right? The next important concept here that we need to understand is, if you're able to calculate the number of field lines per unit area, see, suppose, imagine you have seen this kind of a broomstick, right? Right? My drawing is bad, but yeah, you would have seen these kind of broomsticks which are used to generally clean the outside areas. In parks and all, they use it. No? So if you look at this kind of a stuff, look at this point, that is point number 1, and look at point number 2. If at both the places I consider the same area of cross section, then where is the density of field lines more? So obviously at 1, right? So if you are able to calculate the number of field lines at a particular area, and if that comes out to be a greater value compared to any other point of the same area, then you say at that point, the strength of the electric field is more. Okay. So what I'm trying to say is the number of field lines per unit area at a given point will speak about whom? Will speak about the strength of electric field at that particular location. Are you able to understand? So the number of field lines per unit area, this is the pointer, this is written. See. The number of lines per unit area Through a plane. Plane means area. Through a plane at right angles to the line. To a plane at right angles to the line is proportional to the magnitude of electric field. So I hope you're able to understand the meaning of it. Right? So proportional in the sense, more is the density, more will be the magnitude of electric field. That's it. Okay. So this has a very important name, which we'll be seeing it in the subsequent topics. Okay, these number of field lines to a unit area has a specific name called as flux. Okay. So we'll see about that in the subsequent topics. Just a minute. So with the basics of all the points that we have discussed till now, we'll go on to the next topic, which is called as electric dipole or electric dipole moment. Please write down the heading. Okay. So you talk about an electric dipole, right? The name itself is suggesting electric refers to charge, di refers to two, pole refers to polarity. If you try to bisect the name, electric refers to charges, di refers to two, and pole is a name derived from polarity. So if you are able to have a system of two charges, and how are they supposed to be? They should be of equal magnitude and opposite nature. So what do I mean by that? You should have a system of positive and negative charges. But if you can ask me a question, sir, if I have a system of two positive and a negative charge, can I call it as a dipole? The answer is no. It needs to satisfy something else. What is it? The distance between the distance between the positive and the negative charge should be very small. So when I say very small, it should be in terms of few angstroms or nanometer, because this concept is not something which you can see. Rather, there is a concept which is applied in chemistry. I talk about electric dipole. You talk about the dipole moment in chemical bonding, right? Right. That will tell you whether a bond will break or not. So it has something to do with this concept. So when you talk about a molecule, what is generally going to be the size of a molecule? It is going to be in terms of few nanometer or angstrom. That is the reason why this condition has to be satisfied for that kind of unlike charges to be called as an electric dipole. Am I clear with this? So please write down the definition and underline the important points. Two equal and opposite charges separated by a very small distance constitute an electric dipole. So they constitute an electric dipole. So examples of such dipoles are water, ammonia, carbon dioxide, and chloroform molecules. These are all the examples of molecules with permanent dipole moments. Right. So basically, they'll be called as polar dipoles and non-polar dipoles. Okay. Polar is something which has a net dipole moment. Non-polars are the ones which have zero dipole moment. That is, the dipole moment get cancelled out. Anyways, I'm not getting into the chemical details of it. I'm only looking into the physical aspects. The next concept that you need to understand is dipole momentum. So dipoles have a specific parameter associated with them called as dipole moment. What does it mean? Let us assume you have a system of charges plus q and minus q. Okay, and let's say they are separated by a very small distance 2d, then if you are able to define a quantity which is a product of magnitude of either of the charges, that is Q, into the distance of separation between them, then this particular parameter is called as dipole moment. Now comes an important question. So I understood the mathematical definition of it, but is it a scalar quantity or a vector? Does dipole moment have direction associated with it? Think about it. No? Actually, it is a vector quantity. Because the dipole moment of a particle or a molecule is defined from negative charge towards positive charge. It is exactly in the direction opposite to electric field. That is how it is defined. Okay, how is it defined? Dipole moment is directed from negative to positive charge. I mentioned that point. So I hope you have written this right. Dipole moment. What is it? Magnitude of either of the charges. That is, it can be magnitude of plus q or magnitude of minus q. Right? Magnitude of either of the charges multiplied with whom? The distance of separation between them. So generally, how do we take the distance of separation? We take it as d, no? But here, how is it taken? Here, you have not taken it as d. Look at it. I have circled it. You have taken it as 2d. There is a reason why we have done it. Okay, you will see it in the derivations. So what I'm trying to tell you here is, don't memorize the formula like q into 2d. Don't do that. You should know what is the charge. You should know what is the distance of separation between them. If you know these two values, just multiply. That is how you need to remember, because there are certain problems where they'll not give you 2d and confuse you. What you will do by default, you will put the 2 and get the answer. It will get double the dipole moment, which will go wrong. Okay, their job is like that. So please have this in mind. Next is, it is a vector quantity, and how does it act? It acts from the negative to the positive charge. Now comes an important question. Non-polar. The net dipole moment will be so. The structure of the molecule will be in such a way, because the dipole moment is directed from negative to positive charge. No? So wherever negative charge is concentrated, from there when you try to direct it, they get cancelled out. For example, carbon dioxide. It's a linear structure, right? So oxygen has two lone pairs of electrons. So it is directed towards carbon. They get cancelled out. That is why it is a non-polar molecule. Right? What was I telling? Yeah, it is a vector quantity directed from negative to positive charge. The next question is, what is going to be the unit of it? It is Coulomb meter. Generally, what happens is when we write C, we'll write small c. When we write it faster, don't make the mistake. If you write small c there, it becomes centimeter. Okay, that mistake also happens. I've seen it in many papers. Don't do that mistake. So write it as Coulomb meter. That is in terms of chemistry. Here we define it in terms of Coulomb meter. Right? So I hope you are clear, right? We have set the context. So how did we come? How is the chapter designed? First, we understood what are charges. Then we saw how two charges will interact. Then we saw how multiple charges will interact by using the principle of superposition. Then what did we do? We went into electric field and electric field lines. We understood the properties of electric field lines. And what are the next concept we discussed? Electric dipole. Now, for this electric dipole, our job is to find what is the electric field due to the system. So I told you in the beginning of the chapter itself, wherever the question is related to force, right? What are the minimum number of charges you need? Minimum is 2, maximum can be any number, right? Whereas when you want to define the electric field for a system, what are the minimum number of charges? 1. So the system contains 2 charges, right? So each charge will contribute to individual field, and we need to calculate the total field using vectors. Why is it so? Because electric field is a vector quantity. Are you able to understand? So based on that, what we are going to do is we are going to derive an expression for electric field due to whom? Due to a system called as an electric dipole at 2 important points. One point is called as axial point, and the second is called as equatorial point. It is not equilateral, it is called equatorial. I'll tell you what is the difference. Okay. Shall we get started? So I've given something like method of approach because there's notes which I typed. Right. So I'm directly getting into the context. Let's use the logic and derive it. So what happens? What is the heading? Please write down the heading, guys. Topic number 15. I hope everybody has written the date, right? So under today's date, what are the topics we discussed? Electric dipole, and we are discussing the electric field due to an electric dipole at an axial point. Shall we start? Okay. See, one thing that is easy is the names will suggest you something. Axial, where is it derived from? Axial, the name itself is suggesting along the axis. Axis is what? A line. Now you can ask me a question, sir, if I have a dipole, how do I define the axis for it? Right. So that is what we need to understand first. Even before we start the derivation, the first thing that we need to answer is how do I define the axis of it? Shall we get started? Listen. I have a system of positive and negative charge of equal value. And what is the distance of separation between them? 2D, right? So it is 2 multiplied with D. Now comes an important question. I ask you what is axis? So axis is basically a line, an imaginary line, which passes through both these charges. In the sense, if I take an imaginary line and join both these charges, then I will have a line which is extending in both the directions. But what is the topic? They didn't say axis. They told axial point. So axial point is a point on the axis. So if I take any point P on this axis, my job is to find what is the electric field at that point due to a system of 2 charges. Now I'm not going to anymore look at it like a dipole. I know the dipole will consider a positive and negative charge, the distance is 2D. But now I'll start thinking in terms of individual charges by taking the distances of those charges from point P. Does it make sense? You're able to understand what I'm trying to do? Right. So I told you, right, why we have taken 2D is because wherever dipole, whether it is an electric dipole or a magnetic dipole that is getting involved, all the distances with respect to every point is measured from the center of the dipole. Where is it measured from? It is measured from the center. Center is exactly the midpoint. So if you take this to be the center, then how you break the distances on either side of it? DD, right? That is the reason why we have taken it as 2D. So you can ask me, should I take it only as 2D? No, if you want, you can take it as D also. But you will have a headache of D by 2 on this. So when you're solving, it will become a headache. Just to avoid that only, we have taken this. Okay. Some books, instead of giving 2D, they'll give you 2A. It's up to them. Okay. Now, from here, let me say this distance is R. From where? From the center to the point where I'm trying to calculate the electric field. I'm calling it as R. But for me to calculate the electric field due to a point charge, what is the basic equation telling me? What is the electric field due to a point charge? Please check your notes. Neeraj, did you have it? Huh? Please check your notes and tell me. You call it as KQ divided by R square. We derived it, right? So what does that R stand for? Does that R will be same as this R? R plus D square. R is the distance from that particular charge to whichever point you're trying to talk. So I need to break these distances. So how much will this distance be, guys? R minus D. The distance from the positive charge to point P is going to be R plus T. So can I take something like this? So I am comfortable by labeling the charges as 1 and 2. So if I take at point P, look at the way I'm going to solve this. Okay, I'm treating it like a problem. I'm not teaching as a derivation. If this is a problem, how you are supposed to think. At point P, electric field due to the charge at first position is what? Just so you guys told me, it is 1 divided by 4 pi epsilon naught Q divided by R square. But what is R from the positive charge to the point P? R plus D the whole square. Okay. But I told you one important point at the beginning. Electric field is a vector quantity. So whenever I deal with vectors, right, first thing that I do is I'll concentrate on its magnitude. Then only I'll start thinking of its direction. Now I'll put an arrow mark on top of it. Now I'm concerned or I'm forced to write the direction. Right? I open a bracket. Now I need to think. So what should be the unit vector I need to write? So from the origin, if you call this direction as r cap, you write it as r cap. So before you write the unit vector, whenever you're writing a random unit vector, because r cap is some random number, I cap, j cap, and k cap are universally followed. They are orthogonal unit vectors, whereas r cap is something general. So you need to define it in the problem even before you start. So I write it as r cap. Why did I write it as r cap? Because look at the nature of the charge that is there. For a positive charge, what is the direction of electric field at that point? Is it away or towards? Away. That is the reason I wrote. So my positive charge is on the left, point P is on the right. So away from point P means towards the right. Using the same logic, if I have to write E2, then tell me guys. E2 is equal to 1 divided by 4 pi epsilon naught Q divided by R minus D the whole square. I expected one important question. At point 2, what charge is there? Why didn't I put a minus sign? Because when I'm dealing with vector quantities, this is a very important point. Okay, when you're dealing with vector quantities, when you're writing the magnitude part, just write everything in positive sign, because whatever you're going to put in the bracket will take care of direction. Now what I'm going to do is, due to the negative charge, what is the electric field at point P? Means if I place a test charge at point P, which direction will it tend to move? So this is minus r cap. If one direction is positive, other is negative. So minus r cap when it is written as E2 vector. So the minus sign has come there. Does it make sense? Somebody has asked a question. You don't understand r plus d? Okay. Listen. Just tell me a yes or no, okay?
Yes.
Yeah. So this distance is r. Did you understand that? I'm circling.
Yes, I understand. Yeah. Yes.
Okay, you understood this. This is r means this distance is d. This distance is d. Okay.
Yes.
If this is r, then if this distance is d, if I add both, I'm going to get r plus d.
Sir, isn't it 2D because okay. Yes, yes, I got it.
Got it?
Yes.
Yeah, perfect. So that's the physics part is done. The next step is applying, what is it? Principle of, what should I write? The net electric field at point P is equal to E1 vector plus E2 vector. See, I didn't write it as minus. I wrote it as plus E2 vector because I know within E2 vector that minus sign will take care of itself. So this is equal to 1 divided by 4 pi epsilon naught into Q. I keep it as a constant. I took the whole parameter outside. What is left inside, guys? 1 divided by R plus D the whole square minus 1 divided by R minus D the whole square. This everything in R cap except where this one. Principle of superposition. So the minus of the R cap came. The minus from the R cap has come in. Now it's simple, right? Now it is only mathematical part. So Q divided by 4 pi epsilon naught into, listen to this carefully, okay? If I take LCM, what am I going to get? R minus D the whole square minus of R plus D the whole square, the whole divided by R square minus D square, the whole square times R cap. Am I clear? So A minus B the whole square minus A plus B the whole square. What is it? Minus 4AB. Minus 4. So Q divided by 4 pi epsilon naught into minus 4 into R into D, the whole divided by R square minus D square, the whole square times R cap. Let me call this as equation number 1. Okay. So I would suggest write it down parallel, for the space is less. So till this step, is there any doubt? Right? Science part and mathematics part both are clear, right? Shall I proceed to the next step? Think about it. Just a minute. Yes. Now let's think of this fact. I told you in the beginning of the definition of dipole. What did I say? Distance between them is very small. So you took that r, right? R is distance measured from where? From the center to point P. Now, the point that you need to have in your mind is R is very much greater than D. Okay. In such a way, R square minus D square is approximated to R square. So when you put this two greater than symbol, right, you call it as very much greater than a particular value. For this kind of an inequality, if you square and take the difference, it will always be the value of biggest number. So R square is a very big, see R itself is greater than D. See, for example, 2 is greater than 0.0001. Then what will happen to 2 square? 4 will be very much greater than that. So that if you take the difference between both, what will happen? The difference will be approximately 4. That is what I'm trying to say by this mathematical equation. So R square minus D square is approximately R square. If I take this and substitute it in the above equation, then what am I going to get? Q divided by 4 pi epsilon naught into minus 4 into R into D, the whole divided by R square minus D square is R square. So R square, the whole square will give you R power 4 and you have an R cap. So R and this will get cancelled, right? So listen, I'm pushing this minus sign to this R cap itself. Then what will I have as the magnitude part? 4QD, right? 4QD, see, look at the way I'm writing. 2 into 2Q into, or I'll write it like this. 2 into Q into 2D. Can I write it like this? The same thing. I've broken that 4 into 2. Which one? D divided by R power. Because you're multiplying there. The multiplication operation is different. Okay. But here I'm not approximating R minus D as R. I'm saying R square minus D square is approximately R square. That is one of the things. Okay. See, for example, 2 into 0.001 is a still measurable number. So divided by 4 pi epsilon naught R cube with a minus sign. Accepted? So this is the value of net electric field and vector quantity. Now see what I'm going to do is, what does this Q into 2D stand for? According to the definition, so did they give you the symbol used for dipole moment? It is P. Did you guys write it down? Yeah. So this is 2P divided by, don't be in a hurry to cancel 2 in the numerator and denominator. 2P divided by 4 pi epsilon naught R cube into minus R cap. So yeah. Now you can ask me what is this minus R cap? For that, I need to revisit the diagram. See, if I have a positive charge here, negative charge here, when I took this side direction as R cap, what is the direction of dipole moment? Dipole moment is from negative to positive charge. So if I call this as P cap, then what is the relation between P cap and R cap? So can I say dipole moment cap is equal to negative of R cap? Are you able to understand what I'm trying to say? So R cap and P cap, they both are in opposite direction in this scenario. So having said this, can I write this minus R cap as P cap itself? Then what will happen? 2P divided by 4 pi epsilon naught R cube times P cap will be the net dipole moment due to whom? Due to an electric dipole at an axial point. Okay, at an axial point. So this is the mathematical expression you're expected to remember. So 2P divided by 4 pi epsilon naught R cube times P cap is the answer. So an important conclusion that we can draw here is dipole moment is always, sorry, not dipole momentum. Electric field along axial point is always, sorry. Electric field along the axial point, I've already written. Electric field along the axis is always in the direction of dipole momentum. Always in the direction of dipole. Okay, this is an important point. So they can ask you, the electric field due to a dipole along a particular direction is always in the direction of dipole. So where is the point? You cannot cancel P. But the first P that you have written is magnitude. Second P is direction. That's not easy. You can do that, but you're saying P vector divided by magnitude of P vector. We need not cancel. If you do that, then what is the purpose of? See, the whole objective here is to derive the electric field in terms of dipole moment. Why do you want to cancel? Okay.
Sir?
Yeah, please tell.
Sir, can you scroll up a bit?
Yeah, to which line?
Yeah, sir. Yeah.
Okay. I hope this derivation is clear, right? Just take a minute, go through it. If there is any doubt, get it clarified.
Yes, sir, it is clear.
Okay, done? Okay. So the next heading that you need to write down is derive. That is, we are going to derive the expression due to the same electric dipole, but instead of axial point, we are going to derive it along the equatorial point. Not, I would not say along, I would say at. So whenever we use the word point, we need to use the word at. When you're using line, you call it along. It can be in between also. You will get the same answer. Wherever you have, you can do it. So it's a good question. He is asking, sir, is it necessary that whenever I say axial point, should it be only outside the dipole? Can't it be in between the charges? The answer is it can be. If you want, you can derive it. But here what will happen is, oh, sorry, one more. I'm sorry, it cannot be. It cannot be because the dipole itself is very small. Because you're getting the final expression only because of R very much greater than D. It cannot be in between, but there are certain problems where they will ask you this kind of a scenario. But that will not be an electric dipole, it will be a system of positive and negative charge, because the distance between them will be in terms of 2 meters. Okay. I hope I'm clear, right? So next is we need to derive an expression for the electric field due to an electric dipole at a point on the equatorial line. So what is an equatorial line? That's what we need to understand. So even before I start the derivation, we need to understand certain terms. So what did I call this as? There's an axis. Video is not working. Okay. So this is called as an axis. So if you are able to define a plane, perpendicular to the axis and passing through the midpoint on the axis, you call this plane as equatorial plane. Everyone understand? So what did I say? If you're able to define a plane, plane is a two-dimensional. You take a paper and just place it perpendicular to the axis. At the same time, it should pass through the center of the dipole. Then you call it as equatorial plane. So if you draw the axis of the equatorial plane, it will always pass through the center of the dipole, and this is called as equatorial axis. So basically, plane is two-dimensional, axis is one-dimensional. So on this equatorial axis, if you are able to define a point, okay, then that point is what is called as equatorial point. So plane is two-dimension, axis is one-dimension, point has more dimension. That is how we broke it. Right? Plane is two-dimensional. There is only one equatorial axis. Equatorial axis should always be perpendicular to the axis of the dipole. So you're saying this direction. It can be. But here we are taking it in y-axis. Equatorial plane is a plane, the two-dimensional plane, which is perpendicular to the axis of the dipole and passing through the center of the dipole. So if this is the equatorial axis, you're asking for example. Example is like that. There is no example. You take a dipole, just place your hand like this, perpendicular. So if your hand is able to pass through this, like this, something like this. Okay, this is what is equatorial plane. You're not placing, it's all imaginary. You know? It is an imaginary plane. Axis also, will you sit and draw? Do you think you're going to have a line? No. Molecules are there, that's it. If I have to give a name to that particular line, I'll call it as axis. That's it. So it is not like you're going to take a plane and cut it. No. Don't imagine it like that. Okay. So on this equatorial point, our job is to derive the electric field. So for that, what I'm going to do is positive charge, negative charge. And if I take the distance between them as 2d, so let this be q and let this be q. Okay. So if I take this point as p, okay, where are the distances measured from for a dipole? Always measured from the center. So this is r. Okay. Then this distance is d. This distance is also d. So due to the electric field due to the positive charge is going to be in which direction? Away from it. I'll call it as E1. The electric field due to a negative charge is towards it, which I will call it as E2. So if I have to write the magnitude of E1, what is it going to be? This is R, this is D, then how much is this distance? Root of R. And this one is root of R. Clear? So E1 is equal to 1 divided by 4 pi epsilon naught into magnitude of charge Q or positive charge divided by R square plus D square. The root is gone. Similarly, if I take the electric field due to the second, it is again 1 by 4 pi epsilon naught into Q divided by R square plus D square. So what is the important conclusion you're going to draw? Magnitude of E1 and magnitude of E2 in this scenario is the same. Right? So E1 is exactly equal to E2. And if I say that this is equal to E, you would understand. Now comes an important question. At point P, my job is to derive the net electric field at the point P. In the previous case, our life was simple because they acted along the same direction. So when you did the vectorial addition, your job was only to take less and minus sign property. Whereas here, what is happening? They are acting in some random direction. So E1 is in the northeast direction and E2 is the southeast direction. So it is going something like that, right? So when that is a scenario, we need to bring a common ground to it. For that, what I'm going to do is, I'll draw a separate diagram that is like a free body diagram of these two, where I know the magnitude of these two charges. Now I'm going to take this angle as theta. So if I take the base angle as theta, it forms an isosceles triangle. You're able to see that. So when that is going to be theta, then how much is going to be the angle between these two? So if I call this as alpha, exterior angle is equal to sum of opposite interior angles. So this is going to be 2 theta. Right. If this is going to be 2 theta, then the parallelogram law of vectors tells us an important phenomenon. What is it? Very good. Both of you told the same thing. When both the magnitudes are same, the resultant will always be an angular bisector. So when I say angular bisector, it is going to be something like this, where this is also theta and this is also theta. When that is a scenario, observe, if I take this angle to be theta, then if this is theta, can I say that the resultant is parallel to the axis of the dipole? Accepted. When that is a scenario, then E can be resolved into two components. One is E cos theta and the second is going to be E sin theta. Similarly, this E is going to be E cos theta and this is going to be E sin theta. Which component is going to get cancelled out? E sin theta is gone because they both have same magnitude and opposite direction. So what is going to be the net? What is going to be the net electric field in this scenario? So 2 times E cos theta is going to be the net field. And observe, I'm only, see, till now I concentrated only on magnitude. Till now I didn't touch direction at all. Okay. So 1 divided by 4 pi epsilon naught. What is the magnitude of E? Q divided by R square plus D square. Then what about cos theta, guys? So when I say cos theta, P, if I say this is A and D, let me call this as D, can I take the triangle P, D and A, and if this is taken as theta, then this distance is D and this is R, this is root of R square plus A square or D square. Then what is going to be the value of cos theta, guys? Very good. So D divided by root of R square plus D square. Okay. D divided by root of R square plus D square. So what will be in the numerator? 2Q into D divided by 4 pi epsilon naught into R square plus D square, the whole power 3 by 2. So, but what did I tell you in the previous scenario? R is very much greater than D. R square minus D square is approximately R square. Same is going to be the scenario with plus also. So whether you add or subtract a very small value to a very big value, it is going to get you the bigger value. So what can I approximate this to? R square, but R square, the whole power 3 by 2 is R cube. So 2Q into D is P divided by 4 pi epsilon naught R cube is what is the electric field along equatorial plane, and this is the magnitude. Now I am concerned about direction. So E equatorial, I need to write it in the vector form, which is P divided by 4 pi epsilon naught R cube. Then what will I get here? I don't know. I have to check. So if you see, electric field in this scenario is rightward direction, whereas the dipole moment is in this direction. So P cap and this is R cap. So P cap is negative of R cap. So can I write it as minus P cap itself? because I want the unit vector to be in terms of dipole moment. Okay. Is that clear, guys? R power? See, R square plus D square is approximated to R square. So R square power 3 by 2 is how much? R cube. Correct? So this is what happens. So what can you say about the equatorial point? Electric field at an equatorial point is always in what? In the direction opposite to the dipole moment. So please make a note of it. Electric field at an equatorial point is always in the direction opposite to the dipole moment. Done. Now a last comparison. Magnitude of electric field along axial point is equal to 2 kp by r cube. I wrote it as k directly because k is 1 by 4 pi epsilon naught. Magnitude of electric field along equatorial is kp divided by r cube. So magnitude of axial by magnitude of equatorial is equal to 2:1. So sometimes what they will do, they'll give you the value of electric field along equatorial and ask you to calculate the electric field along axial. You just have to multiply it with E axial is always twice that of equatorial. Correct? Electric field, net electric field is in the rightward direction. Dipole moment is in the leftward direction because dipole moment is from negative to positive charge. That's the reason. So they both are in opposite direction. Speed. You're asking speed. Here it is not going to accelerate or something, right? Why are you concerned about speed? I need your question again. I'm not able to get you. Equatorial point. Okay. Nothing will happen. That's all. It has nothing to do with resisting or something. It is only you're finding the magnitude and direction of it. That's it. Because here everything is under static condition. Why do we need to talk about resistance? Okay. So this is there. So these are the two important derivations with respect to it. So this is the one I wrote. Electric field along axial is equal to 2 times the electric field along equatorial. So the next concept that we need to see is what happens to an electric dipole when you place it in an external electric field, okay, or uniform electric field. Okay. So I don't think I can do it in 5 minutes. I'll just give you the basic introduction of it and revise the concept of torque and tom. Okay. 11 standard videos are there, so you can go through it, revise the concept of torque and tom. So 17th topic, right? Let me read this out. So what is it? Derive an expression for torque experienced by an electric dipole based in uniform magnetic field. First of all, what do you mean by uniform magnetic field? Uniform, the name itself suggests. At every point, it has a same value, a uniform value, right? When you have a set of parallel lines, you call it as uniform electric field. So in the previous two scenarios, what happened is you had an electric dipole and you calculated the electric field generated due to it. Understand the difference? So what was the topic there? Calculate the electric field due to a dipole at axial and equatorial point. But what is the topic here? What will happen if you take the dipole and place it in some already present external electric field? So what is going to happen? This is a question. Right. So uniform electric field is a set of parallel lines in which you are placing a dipole. Let's say you are placing it at some inclination theta with respect to the axis, with respect to the field itself. Okay, who is making an angle? The axis of the dipole is making an angle theta with respect to the electric field itself. Okay, when that is going to be the scenario, then what will happen to it? Okay, the answer is very simple. So if you place any charge in external electric field, first thing is it starts experiencing force. So you have charge, isolated charge, take and drop it in electric field. What will happen to it? It will start experiencing a force of Q into E, accept it. Because E is equal to F by Q, F is equal to QE, right? So the positive charge, which is present here, will start experiencing the force in the direction of electric field, whereas the negative charge that is present will start experiencing the force in the direction opposite to the electric field. Now comes an important question. What is going to be the net force experienced by this system? What is going to be the net force experienced by this system? Net force is 0. Right? That is why if you see the heading carefully, what are they saying? They have an expression for torque. They didn't say about force. Because the net force is going to be 0. Now you can ask me, how is torque going to act? So it is a very simple thing. What actually does it form? It forms something called as a couple. You've heard about this mechanical couple. What is it? So you have a particular object which is subjected to equal and opposite force at the ends of it. It starts revolving. So that's what we call it as a couple. So what happens here is this kind of a dipole will start revolving in the clockwise direction. So how did I conclude clockwise direction? Because QE is in the rightward direction, minus QE is in the leftward direction. So both support each other to put the whole system into a clockwise rotation. So our job is to calculate what amount of torque will this kind of a dipole experience. Okay, which we will see in tomorrow's class. Right. So here I'm talking about uniform electric field, right? We need to also think of what happens when it is non-uniform electric field. And I'll tell you an application of why we are studying this also. Okay. So is there any other doubt from today's class? Because look at the direction. Yeah, tell me about.
Sir, for like while calculating for axial point, we have considered the we have considered the direction before calculating the net value, sir.
I'll tell you.
But
That is what I'll tell you. I understood your question. Why I did it there is because in the case of axial, are you able to see the screen? In the case of axial, both the electric fields were anti-parallel to each other. So our job was easy because there was a difference of only minus sign. You're able to understand? In terms of direction. Whereas in the case of equatorial, what has happened is if I consider this as R1 cap, I have to consider this as R2 cap, and R1 cap and R2 cap have no relevance between them, which would have become a tough factor for us. That is the reason I didn't consider the direction. Okay, so whenever you have this kind of a scenario, it is always advisable to go with resolution of vectors. Don't go with direct vectors. It will be a tedious process unless you are very good with angles and everything. Okay, I'll not suggest at all. So go with the concept of resolution. Did I answer your question?
yes, sir.
Yeah.
Thank you, sir.
You were asking something. What is it? Yeah. How did you got the answer? Because of the direction. Simple. I apply a force in this direction. How is it clockwise? Okay. So there's actually a simple derivation, but time is not sufficient. After this, we'll go to the next concept of electric flux. Then we'll go to an important concept called Gauss law and its applications. With that, we are done with this chapter. Okay. I hope till now it was easy only, right? Is there anything that is complicated? It's an easy chapter. So just keep revising, that's it, before you come to the next class. That's it, right? So guys who are online, any doubt?
No, sir.
Okay, perfect. We can wind up then.
Thank you, sir.
Thank you, sir.